A photon born in the core of a star the moment Earth formed could still be flying through space right now, unchanged, carrying the same energy it left with 4.5 billion years ago. Its internal clock has not ticked once. Not a single second has passed for it. We're going to follow one of these particles from the instant of its birth, through a universe that tries everything it can to destroy it. Walls, black holes, the stretching of space itself, and ask whether anything in physics can actually kill light. If this fascinates you, hit subscribe so you don't miss where this leads. Now hold your breath. We begin. Deep inside an atom, something shifts and light is born. Picture a single electron orbiting a nucleus. It sits in a particular energy level, a kind of invisible shelf around the atom. These shelves are fixed. An electron cannot hover between them. It can only occupy one shelf or another, never the space in between. This is one of the strangest rules in physics, and it is the rule that makes photons possible. Now imagine the electron gets a nudge. Maybe a passing particle strikes it. Maybe the atom absorbs heat. Whatever the cause, the electron jumps to a higher shelf further from the nucleus. Up there, it is unstable. It wants to fall back down to where it was, and when it falls, it has to release the extra energy it was carrying. That energy cannot simply vanish. The universe does not allow that. So the atom does the only thing it can do. It spits out a tiny packet of pure light. That packet is a photon. The moment of its birth takes less time than you can imagine. We're talking about an interval so short that if you stretched it out to 1 second, a single second of ordinary time would stretch longer than the age of the universe. In that unimaginably brief flash, a photon leaves the atom carrying a very specific amount of energy, determined by exactly how far the electron fell between shelves. A short fall makes a low-energy photon, maybe infrared light you would feel as warmth. A long fall makes a high-energy photon, maybe ultraviolet, maybe an X-ray. Here is where things begin to feel strange. The photon does not drift away from the atom the way smoke drifts from a candle. It does not gradually build up speed. It leaves at the maximum speed the universe permits, already at full velocity, from the very first instant of its existence. There is no acceleration, no warming up, no process of getting going. One moment there is no photon. The next moment there is a photon, moving at 300,000 kilometers per second, or about 186,000 miles per second exactly. Think about what that means. Every photon you have ever seen, every photon that has ever entered your eyes from a lamp, or a screen, or a distant star, came into existence already at that speed. A particle cannot simply appear in motion, yet photons do. They are born running, and they keep running. Unless something stops them, they will continue forever in whatever direction they were emitted, carrying that exact energy, that exact frequency, that exact information for as long as nothing interferes. The atom that made the photon may itself be destroyed by a supernova, swallowed by a black hole, or simply wait for billions of years until the cosmos cools into silence. None of that will reach the photon. The photon will have already left, already on its way, already indifferent to the fate of its birthplace. So the first question becomes simple. If a photon is born at maximum speed, carrying a fixed amount of energy, with no friction to slow it down and no engine to wear out, what would it even mean for such a thing to die? Before we can answer that, we have to understand the single strangest fact about photons, the one that separates them from every other particle in existence. They have no mass. A photon has no mass, not a little mass. not an almost undetectable amount. 0. This is harder to swallow than it sounds. Everything you've ever touched, lifted, dropped or weighed has mass. A grain of sand has mass. A speck of dust floating in a sunbeam has mass. Even a single atom of hydrogen, the lightest atom in the universe, has mass. Mass is what makes a thing feel like a thing. It is what lets you push something and feel resistance, what makes objects fall, what gives the world its solid, stubborn presence. Now try to imagine a particle that has none of that. A particle that, if you somehow held it in your hand, would not press down on your palm with any weight whatsoever. A particle that no scale, no matter how sensitive, could ever register. That is a photon. But the word massless can mislead you. It does not mean the photon is nothing. Photons carry energy. They carry momentum. A beam of sunlight pushes on a solar sail and actually moves it. If you stood on a windless day in the vacuum of space and pointed a powerful flashlight forward, you would slowly drift backward, pushed by nothing more than the light streaming out. The photon has punch, just has no weight. How can something have momentum without mass? This is one of the places where the physics you learned in school quietly breaks down. In the everyday world, momentum is mass multiplied by speed. A heavier truck has more momentum than a lighter car at the same speed. By that rule, a massless particle should have 0 momentum, no matter how fast it moves. 0 times anything is 0. The escape from this paradox lies in a more complete equation, one that connects energy, mass, and momentum together. In that deeper equation, a particle's energy comes from 2 sources. One source is its mass, the famous mass-energy equivalence. The other source is its momentum. For ordinary matter, the mass piece dominates. For a photon, the mass piece is simply absent, leaving only the momentum piece. All of a photon's energy is motion energy. It exists because it moves. It cannot stop, because if it stopped, it would have no energy left, and with no energy it would cease to be. That is the deepest meaning of masslessness. A photon is a particle whose entire being is bound up in its motion. Take away the motion, and you have not slowed the photon down. You have erased it. Compare this to you. If someone froze you in place, you would still exist. Your atoms would still be there, your mass still pressing on the floor, your shape still visible. Motion is something you happen to do. It is not what you are. For a photon, motion is what it is. Stopping a photon is like asking a flame to exist without burning. This is why photons travel at the speed limit of the universe and nothing slower. They have no rest state to return to. They have no option of pausing for a breath. From birth to destruction, every photon is always moving, and always at the same speed. That speed hides a secret stranger than the masslessness itself. We call it the speed of light. Every physics book prints it the same way, a number attached to the motion of photons through empty space. But the name is misleading. The speed of light is not really the speed of light. It is the speed limit of the universe, and photons just happen to travel at it. Here is what that distinction means. Imagine the universe comes with a single, absolute rule, built into the fabric of space and time itself. The rule says that no information, no signal, no cause and effect can travel faster than a certain maximum rate. That maximum rate is a property of reality, not a property of any particular thing. It exists whether or not anyone is using it. It would be there if there were no photons at all. Photons happen to travel at that maximum rate. So does every other massless particle the universe allows. If there were no photons and only some other massless particle existed, that particle would travel at the same speed. The speed is not set by light. Light is set by the speed. This reversal changes everything. For centuries, people thought light was something that moved through space, like a ball rolling across a field. If you threw the ball harder, it went faster. If you threw it while running forward, your speed added to the ball's speed. This is how the everyday world works. But light does not obey this rule. If you shine a flashlight forward while running toward a target, the light does not arrive faster than it would have if you were standing still. The light moves at its fixed speed no matter what you do. Scientists tested this over and over, trying to catch light cheating. They set up experiments where the Earth's motion around the sun should have added to or subtracted from the speed of light reaching a detector. They measured very carefully. The speed never changed. Not a little, not at all. Light travels at exactly the same speed for someone standing still, someone flying in a jet, and someone riding on a spacecraft headed the other direction. This was so strange that Albert Einstein had to rebuild the foundations of physics to make sense of it. He realized that if the speed of light is truly constant for everyone, then something else has to give. What gives is time itself. Clocks on a moving rocket tick slower than clocks on the ground. Rulers on a fast spaceship shrink in the direction of motion. Space and time warp and stretch to protect the speed limit. The speed stays fixed. Reality bends around it. And sitting right at the top of that speed limit, every single photon races through the cosmos. From the dimmest radio wave to the most violent gamma ray, they all travel at exactly the same speed through empty space. A red photon and a blue photon released at the same instant from the same place will arrive at a distant target at the same instant. Color does not change speed. Energy does not change speed. Nothing the photon does changes its speed, because its speed is not really its choice. It is the speed the universe allows, and the photon has no room to be slower. A consequence of riding at this speed is something almost no one is prepared for. Time, for the photon, does not pass. Einstein discovered something about moving clocks that still unsettles physicists a century later. The faster a clock moves, the slower it ticks. This is not an illusion. It is not a mechanical problem with the clock. Time itself slows down for anything in motion, and the faster the motion, the greater the slowing. At ordinary speeds, the effect is too small to notice. A jet airliner flying for 10 hours arrives with its clocks about a billionth of a second behind clocks on the ground. Real, measurable, utterly tiny. But as you approach the universal speed limit, the slowing becomes extreme. At 90% of that speed, a clock ticks at about half the normal rate. At 99%, it ticks at about 1/7. At 99.99%, a second of clock time stretches to cover more than a minute of outside time. Now push the math all the way to the limit. Push the speed of the clock right up to the universal maximum itself. The slowing does not just become large, it becomes infinite. A clock travelling at the speed limit has its ticks stretched out so completely that they never arrive at all. The clock does not run slow, the clock does not run. This is the situation of every photon. From the photon's own point of view, if we can even speak of such a thing, time does not pass. A photon born in the heart of a star 10 billion years ago, travelling through space ever since, has experienced no duration between its birth and this moment. 0 seconds. The journey that took 10 billion years by our measure took no time at all by the photon's measure. The two events, emission and arrival, are not separated by any interval in the photon's own reckoning. They are, in a sense, the same moment. Try to sit with that for a minute. a photon crossing the entire visible universe, traversing a distance so vast that counting the zeros would take all afternoon, arrives at its destination in the same instant it left. The in-between does not exist for it. Space itself, in the direction of motion, collapses to nothing. The photon's universe is flat, a single surface where emission and absorption touch. This is what it means to say a photon has no proper time. Proper time is the time measured by a clock riding along with an object. For you, proper time is just the time you experience as you live, 1 second at a time. For a photon, proper time is always 0, no matter how long or short its journey appears from outside. Notice what this does to the question of how long a photon lives. From our outside perspective, a photon can last for billions of years, streaming across the cosmos towards some distant detector. From the photon's perspective, it does not last for any amount of time at all. Birth and death, if death comes, are simultaneous for it. A photon that travels forever and a photon that travels for a single nanosecond have had the same experience of their own existence. None. This raises a question physicists have argued about for decades. If a photon does not experience time, if its entire life is compressed into a single frozen instant from its own point of view, can we even say a photon exists in the way other particles exist? The answer depends on what we mean by existence. You experience time. You have a past, a present, a future. Your existence unfolds. Each moment of your life leads to the next, and the connection between those moments is part of what makes you you. A photon has none of that. From its own frame, if such a frame even exists, there is no unfolding, no sequence, no first this, then that. There is only the frozen instant where emission and absorption coincide. So the question cuts deep. Does a photon exist in any meaningful sense between the atom that emits it and the atom that absorbs it? Or does it only exist at those two moments, with the space in between being something we infer but the photon never actually traverses? Physicists have taken different positions on this, and the disagreement is not about experimental data. It is about what the data means. Everyone agrees on the measurements. The photon's energy when it arrives matches what the emitting atom released. The timing matches the distance divided by the speed limit. Detectors click at the moments we would expect them to click if a photon really flew through space. The equations work flawlessly. The interpretation of those equations is where the trouble starts. One view says the photon really does travel through space, moment by moment, just like any other object, and the fact that it experiences no time is just a strange feature of its frame of reference. The photon is a real thing following a real path, and its path happens to have 0 length from its own point of view because of how relativity works. This is the intuition most of us start with, and it is not wrong, but it is incomplete. A second view takes the photon's perspective more seriously. If the photon experiences no time and no distance between emission and absorption, then maybe the emission and absorption are, at some level, a single event. The atom that emits and the atom that absorbs are, for the photon, directly in contact. The path we see is something constructed by our outside perspective. The photon itself is not at any of those intermediate points. It is only at the beginning and the end, which are the same to it. A third view, rooted in quantum mechanics, goes further. Between emission and absorption, the photon does not have a definite location at all. It is spread out as a wave of possibilities, passing through every possible path at once, and only becomes localized when something absorbs it. In this view, asking where the photon was during its journey is asking a question that has no answer. The photon was not anywhere in particular until it was detected. Each view captures something true. The photon really does affect the world between emission and absorption. Its energy and momentum have to be carried somehow. But the photon also has no proper duration, and possibly no definite position during its flight. It is a carrier of energy and information across space, without fully being a thing in the way a rock or an atom is a thing. This ambiguity is not a flaw in our theories. It is a feature of what photons actually are, and it has a practical consequence. When we try to measure how long a photon can live, we are asking a question the photon itself would find meaningless. If a photon does not experience time, how can anyone measure how long it lives? This sounds like a paradox, but physicists have found a clever way around it. They do not ask the photon, they ask us. From our outside perspective, photons absolutely can be timed. A photon from the Sun takes about 8 minutes to reach Earth. A photon from the nearest star beyond the Sun takes about 4 years. A photon from a distant galaxy might take billions of years. These are all real, measurable durations in our frame of reference. Even if the photon feels nothing, we feel the weight. So the question becomes whether a photon, if left undisturbed, simply travelling through empty space without being absorbed or scattered, can survive indefinitely from our point of view, or whether there is some internal clock inside the photon itself, ticking down toward an eventual decay, a moment when the photon would spontaneously fall apart into something else. If photons have a finite lifetime, we should be able to see the evidence in the oldest light around us. The universe is filled with leftover radiation from its early days, a faint glow of microwaves reaching us from every direction. This radiation has been travelling for over 13 billion years. If photons decayed with any significant probability per year, a noticeable fraction of that ancient light should have vanished by now. The sky would be dimmer than our theories predict. The spectrum of the leftover glow would be distorted in characteristic ways, with certain wavelengths missing or reduced. Scientists have measured that ancient radiation with extraordinary precision. Satellites have mapped its spectrum, its temperature, its tiny ripples, and found it matches the predictions of a universe where photons are stable. No dimming beyond what expansion already causes, no missing wavelengths hinting at decay. The absence of these signatures lets physicists put a lower bound on how long photons can survive. The current best estimate, pieced together from these observations, is that a photon's lifetime must be at least around 1 billion years in its own frame of reference. That number is so large it loses meaning. The universe itself is only about 13 billion years old. The estimated lifespan of a photon is roughly 70 million times longer than the entire age of everything that exists. And this is a lower bound, a floor, not a ceiling. The actual lifetime could be much longer. It could be truly infinite. Our measurements cannot distinguish between a lifespan of 1 billion years and a lifespan of forever. We can only say that photons, if they decay at all, decay so slowly that in the time since the Big Bang, we have not seen enough of them die to register any effect. For all practical purposes, within the span of the universe we know, photons are stable. They do not age in the ordinary sense, they do not wear out. A photon released today will, if nothing absorbs it, still be travelling when the last stars have long since burned out and the galaxies have drifted beyond sight of one another. This stability is not an accident. It is a consequence of a deep rule woven into the laws of physics. A rule that forbids photons from decaying on their own. Understanding that rule requires learning about a kind of symmetry most people have never heard of. Every particle that decays has somewhere to go. a neutron sitting alone outside an atomic nucleus will fall apart in about 15 minutes, transforming into a proton, an electron, and a tiny ghostly particle called a neutrino. The neutron can do this because the combined mass of the things it becomes is slightly less than the mass of the neutron itself. The leftover mass gets converted into energy, and the decay is allowed. This is the general pattern. A particle can only decay into other particles if the total energy comes out right, and if the various conservation rules of physics are obeyed. Energy has to balance. Momentum has to balance. Certain other quantities, like electric charge, have to balance too. A decay that would violate any of these rules is forbidden, and forbidden decays never happen. Now consider the photon. For the photon to decay, it would have to turn into something else, something with less total mass and carrying the same energy, momentum and charge. But here is the first problem. The photon has no mass. There is nothing lighter than no mass. The photon is already at the bottom of the scale. For it to decay, it would have to turn into particles that are also massless, or particles so light they might as well be. The only other massless particles known to exist in the universe are gluons, which are trapped inside protons and neutrons and cannot exist freely, and gravitons, which have never been directly detected. Neither of these is a viable target for a photon to decay into. Gluons carry a kind of charge that photons do not, so the conservation rules block that path. Gravitons, if they exist, interact so weakly that a decay into them would be impossibly rare, far beyond anything our detectors could catch. But the deeper reason photons do not decay goes beyond this accounting of particles. There is a principle in physics called gauge symmetry, and for photons specifically, it is a symmetry named U1. The name is technical, but the idea behind it is clean. U1 symmetry is a rule that says the laws of physics remain unchanged when certain mathematical quantities are rotated, similar to how a perfect circle looks the same no matter how you spin it. This symmetry is what gives us the electric and magnetic forces, and it is what gives us photons in the first place, and here is the key. For this symmetry to hold, for electromagnetism to work the way it works, the photon has to be exactly massless and exactly stable. If the photon had even a whisper of mass, or if it could decay, the symmetry would break, and the whole structure of electromagnetism would unravel in ways that would be obvious in every experiment we have ever done. We would see electric fields behaving wrong. Magnets would fail in specific measurable ways. Radio waves would not propagate as they do. We've tested electromagnetism to incredible precision, and it works. Every test confirms the symmetry, which means the photon is massless, and the photon is stable, all the way down to the deepest level we can probe. It is not stable because we have not caught it decaying yet. It is stable because decay would violate a fundamental symmetry that nature, as far as we can tell, does not violate. There is still a way to imagine the photon dying, though, if we are willing to break the rules. Physics has a tradition of asking dangerous questions. What if this fundamental law is wrong? What if this fundamental constant is not truly constant? Most of the time, these questions lead nowhere, and the old laws survive another round of scrutiny. But sometimes, very rarely, the questioning opens a door. So let us ask the dangerous question about photons. What would have to be true in the deep structure of the universe for a photon to actually die? The first thing that would have to change is the photon's mass. As we saw, a truly massless particle has no lighter particle to decay into, and the symmetry protecting it from decay is ironclad. But if the photon had even the tiniest mass, a mass so small we have not been able to detect it so far, things would change. The protective symmetry would no longer apply in the same way. The photon would become eligible to decay into any lighter particles the universe contains, and if the photon had mass, it could decay into the lightest particles we know of that are lighter than it. Those would be neutrinos, ghostly particles that barely interact with anything and are believed to have very small masses themselves. A massive photon could, in principle, transform into a pair of neutrinos, one matter and one antimatter, balancing the books. This decay is allowed by the conservation rules if the photon's mass is bigger than twice the neutrino mass. Scientists have searched for signs of photon mass very carefully. They have studied the behavior of magnetic fields across vast distances, looking for tiny deviations that a massive photon would produce. They have examined the propagation of radio waves from distant pulsars. They have measured electromagnetic fields in laboratories and across solar system scales. Every test has come up empty. Every test has pushed the upper limit on the photon's mass lower and lower. The current best experimental limit says that if the photon has any mass at all, that mass must be less than about 1 part in a billion of the mass of an electron, which is already one of the lightest particles we know. At this level, the photon is either truly massless or so close to it that we may never be able to tell the difference. And if the photon does have this tiny possible mass, the resulting lifetime would still be absurdly long, likely longer than anything our universe has yet experienced. But let us push the thought experiment further. Suppose a massive photon really does exist, at the very edge of what experiments allow, and suppose it really can decay into neutrinos. What would happen in such a universe? Every photon that managed to survive without being absorbed would eventually, after an unimaginably long time, just dissolve. Light from the earliest galaxies would fade on its journey bit by bit, replaced by a sea of invisible neutrinos streaming through space. The night sky of a sufficiently old universe would grow dimmer, not just because stars burn out, but because the light already in transit would be actively disappearing. The cosmos would be quietly thinning out, losing its brightness from within. This may still be happening in our universe, very slowly, too slowly to see, or it may not be happening at all, and photons may be truly, perfectly, eternally stable. The line between these two possibilities is the thinnest line in all of physics, and finding out which side we are on is a question that haunts the field. Every particle that decays is, in a sense, looking for a lower resting place. It wants to turn into something lighter, something with less energy, and release the difference as motion or as new particles. This is the general trend of the universe. Things roll downhill. A heavy, unstable particle is a stone perched at the top of a slope. Sooner or later, something nudges it, and it tumbles to a lower energy state. For a photon to decay, it would need a slope to tumble down. It would need something lighter than itself to become. The search for that something lighter has been one of the quieter obsessions of particle physics. At first glance, the scenery looks empty. The photon is already at zero mass. You cannot get lighter than zero. There is no particle in the known zoo of physics that can serve as a lower resting place for a truly massless photon. If the photon has no mass, the slope does not exist, and the photon stays perched at the top forever, because there is no top to fall from and no bottom to fall to. But physicists have not stopped looking. They have considered the possibility that the standard zoo is incomplete, that there might be particles even lighter than neutrinos, so light and so weakly interacting that they have escaped every detector ever built. Some of these hypothetical particles go by strange names. Axions, for instance, are proposed particles thought to be extremely light, possibly billions of times lighter than neutrinos. If they exist, they could, in principle, serve as the lighter end of a photon decay. In some theoretical models, a photon could oscillate into an axion and back, sort of borrowing an identity and returning it, the way a neutrino is now known to oscillate between different types. If this oscillation is possible, then under the right conditions, some fraction of the photons travelling through the universe could temporarily stop being photons. If they are absorbed or detected during that brief change, they would appear to have vanished. Experiments have been set up in caves and tunnels to catch exactly this, shining powerful lasers through walls that ordinary light cannot penetrate, looking for any trace of light reappearing on the other side after converting into an axion and back. So far, no signal. Just tighter and tighter limits on how such a particle, if it exists, would behave. The lighter resting place the photon might fall into, if it can fall at all, remains undiscovered, and without a lighter destination, the photon has nowhere to go. It stays what it is. This result is cleaner than most in physics. It is not that we have searched and come up with reasons to believe the photon is stable. It is that the photon is stable because the universe does not provide an exit door. Decay requires somewhere to decay to. The photon, as far as we can tell, has been given no such place. This is why every experimental test comes back with the same answer. The photon does not decay, and the lower bound on its lifetime keeps climbing. Each year, as measurements improve, the floor rises. The photon keeps passing every test. The exit stays locked. But if a photon cannot decay on its own, the universe has other ways to rob it. And the first of those is the slow, inescapable theft carried out by space itself. Space is not sitting still. It is expanding, and has been expanding since the universe began. Every part of the cosmos is getting farther from every other part, and the expansion reaches into every corner, including the regions where photons are travelling. Imagine a photon released long ago, near the beginning of time, with a particular wavelength. The wavelength is the distance between one crest of the photon's wave and the next. Think of it as the photon's stride. A short stride means a high-energy photon, like an X-ray or ultraviolet light. A long stride means a low-energy photon, like a radio wave or microwave. The stride is tied directly to how much energy the photon carries. Short stride, high energy. Long stride, low energy. Now watch what happens as the photon travels through expanding space. The space the photon is moving through is stretching beneath it as it goes. The wave carried by the photon stretches along with that space. The distance between crests grows. The stride lengthens. By the time the photon reaches a distant detector billions of years later, its wavelength is longer than when it started, and its energy is lower. This is cosmological redshift. It is not a decay. It is not an absorption. The photon is still there, still moving at the universal speed limit, still perfectly intact in every way that counts. But it has less energy than it used to. Some of its punch has been spread out and diluted by the expansion of the cosmos. The numbers are stark. Light from the earliest moments of the universe, emitted when the cosmos was hot and compressed, started out as high-energy visible light. By the time that same light reaches us today, its wavelength has stretched by a factor of about 1,000. It has gone from visible light to microwaves, a dim, cold glow reaching us from every direction in the sky. This is the cosmic microwave background, and it is quite literally ancient sunshine, shifted down into a colder form by 13 billion years of expansion. The photons in that background have not died. They are still here, still flying, still being detected right now by satellites and antennas. But each one of them carries only about 1,000th of the energy it started with. The rest has been stretched out of it, not transferred to another particle, not absorbed by anything, just thinned out by the growing space. This raises a strange question. If a photon keeps losing energy to expansion, does it eventually run out? Can a photon be stretched so thin that it becomes, for all practical purposes, nothing? The answer is that in principle, yes. In the limit of infinite expansion, a photon's wavelength could grow without bound, and its energy could approach zero. But approaching zero is not the same as reaching zero. A photon with extremely low energy is still a photon. It still has a wavelength, still travels at the universal speed limit, still exists. It just becomes harder and harder to detect, and eventually its influence on anything becomes so weak that it is effectively absent. This is not decay, it is dilution. The photon does not disappear in any sudden moment. It just fades, forever. Never quite vanishing, but never recovering either. And the oldest photons in the universe are the ones that have faded the most. Somewhere around you, right now, photons are passing through the walls. Photons older than the oldest star. Photons that began their journey when the universe was 1,000 times hotter than it is today. They have been travelling uninterrupted for about 13 billion years, and every antenna on Earth that knows how to listen for them picks them up as a faint, steady hiss. These are the photons of the cosmic microwave background, and they are the closest thing we have to a photograph of the universe in its infancy. Here is how they came to exist. In the very early universe, everything was so hot and dense that atoms could not hold together. Electrons zipped around freely, unable to settle into orbits. Photons could not travel more than a tiny distance before colliding with an electron and scattering in a new direction. The whole cosmos was like a thick, glowing fog. Light existed, but it could not get anywhere. It was trapped in a jumbled dance with the free electrons. Then the universe expanded and cooled. At a certain point about 380,000 years after the beginning, the temperature dropped low enough for electrons to finally stick to protons and form neutral atoms. The fog lifted. Suddenly, photons had clear space to travel. Every photon that happened to be moving in a direction that did not immediately hit something was set free. Those photons are still flying. Most of them will fly forever, because empty space has very little in it to stop them. And because the universe has been expanding the whole time, the wavelengths of those photons have stretched enormously. What began as visible and infrared light has been shifted down into microwaves. When we point a sensitive antenna at the sky, at the right frequencies, we detect this ancient light coming from every direction at once. There is no gap, no dark spot. The sky is glowing uniformly with ancient photons, all of them released in that brief moment when the cosmic fog cleared, all of them now reaching us as very faint microwaves. The remarkable thing is how perfectly their spectrum matches the predictions of a universe where photons are stable. If photons decayed even a little, we would see deviations. Certain wavelengths would be suppressed. The temperature of the background would not match the calculations. The edges of the spectrum would be blurred or bent. None of that is observed. The measured glow matches to extraordinary precision the prediction for ancient photons that have simply travelled and stretched, unharmed, for 13 billion years. This is, in a way, the strongest single piece of evidence we have that photons do not die easily. The universe has given us an experiment we could never perform ourselves. It has released trillions upon trillions of photons at a known moment in the deep past and let them fly for 13 billion years through the cleanest vacuum imaginable. We can count them, we can measure their energies, we can check their spectrum, and every time we check, the photons are still there. Still cold, still faint, still arriving. Older than anything in the universe except time itself, and still carrying information about where they came from. Which brings us back to the question we keep circling. A photon can survive 13 billion years of travel, stretched and dimmed but unbroken. What happens if we let it travel far longer? What happens when its wavelength grows longer than the observable universe? A photon's energy is tied to its wavelength tightly through one of the simplest equations in physics. Short wavelength, high energy. Long wavelength, low energy. As the universe expands and a photon's wavelength stretches along with space, its energy drops in proportion. Imagine you could watch a single photon travel for a very long time. At first, it loses energy quickly as the universe expands in its early, faster phases. After a few billion years, the loss slows. After tens of billions of years, the photon's wavelength has grown far beyond where it started. After hundreds of billions of years, the photon is carrying so little energy that you could not detect it with any instrument ever built. After trillions of years, the wavelength might stretch across distances larger than galaxies. After far longer still, larger than the observable universe itself. At some point in this progression, you run into a strange conceptual wall. A photon with a wavelength longer than the region of space you can see is, in a real sense, a photon you cannot localize. Waves need room to exist as waves. A wave whose stride is bigger than the room it is in cannot complete a single full cycle within that room. The photon becomes a thing whose signature is spread across more space than is available to contain it. Does such a photon still exist? This is where physicists hesitate. The equations do not predict a sudden end. There is no wavelength at which a photon is declared officially dead. The math simply says the energy approaches zero without ever quite reaching zero. The photon is still a photon in principle, but it is so spread out, so diffuse, so energy poor, that its ability to interact with anything becomes effectively zero as well. It cannot be absorbed, because absorption requires a measurable exchange of energy. It cannot be detected, because detection requires an interaction. It just exists in a ghostly sense, as a wave so faint and stretched that it has no consequences. This is not decay in any ordinary meaning of the word. The photon has not turned into something else. It has not been absorbed. It has not violated any conservation law. But it has been thinned out so completely that it is, for all intents and purposes, gone. The bookkeeper of the universe might still count it as a photon in some abstract ledger, but nothing and no one will ever know it is there. Philosophers of physics have a term for this kind of situation. They call it quiet dissipation. The photon is still present in the mathematics but absent from any possible experience or measurement. It neither lives nor dies in the dramatic sense. It just fades, asymptotically, towards silence. A universe old enough to have stretched its photons to this degree would be a very strange place. Most of the photons from earlier eras would still technically exist, but their total contribution to anything happening in that universe would be zero. The cosmic microwave background itself, still rich today, would be stretched out to the point where each photon covers vast distances and carries less energy than the quietest whisper. The universe would grow cold in a way that is not about temperature dropping, but about the very idea of temperature losing its meaning. None of this is a threat on any timescale we care about. Our sun, our galaxy, our universe as we know it will all be gone long before photons approach this limit. But the limit exists, and it tells us something. Photons are stable, but the space they travel through is not stable in the same way. Space grows, and as it grows, it drains the light inside it. Still, the slow theft of energy by expansion is only one way a photon's career can end. Most photons in practice meet their fate much more suddenly. They are not stretched into invisibility over trillions of years, they are swallowed. A photon's most common fate is not cosmological. It is not anything so grand as being stretched into silence by the expansion of the universe. It is something much more ordinary. A photon ends because an atom absorbs it. This happens everywhere, all the time, around you right now. The light from the lamp above you is pouring out photons by the trillions every second. Some of those photons hit your wall and are absorbed, which is why the wall is not glowing in the dark. Some of them hit your skin and are absorbed, which is why you feel faintly warm under bright light. Some of them hit your eyes, and a very specific, specialized process captures them for vision. Every one of these absorbed photons has ended its career. The photon that was is no longer. The energy it carried has been taken up by the material that caught it. But what exactly happens when a photon is absorbed? The process is strange and reveals something essential about the relationship between light and matter. An atom is capable of absorbing a photon only if the photon's energy matches the gap between two of the atom's energy levels. Those shelves we discussed at the beginning. If a photon comes in carrying exactly the right amount of energy to lift an electron from one shelf to a higher one, the atom will grab it. The photon disappears, the electron jumps up, and the energy is now stored in the atom as excitation. A photon with the wrong energy, one that does not match any available gap, will pass right through the atom without being absorbed at all. This is why some materials are transparent to certain kinds of light and opaque to others. Think about what this means. A photon is not absorbed by every atom it meets. It is absorbed only by atoms that can receive it, only by atoms with an available energy gap of exactly the right size. Most photons passing through most materials simply do not interact at all. Empty space is especially good at letting them through, because there are very few atoms to block them. A photon released into intergalactic space can travel for billions of years before encountering a single atom capable of absorbing it. But when an absorbing atom is encountered, the interaction is sudden and total. The photon does not slow down, it does not fade, it is there, and then, in less time than any clock could measure, it is gone. The atom has taken up the energy, the photon has ended. Here is the deepest fact about this. The photon does not leave remains. It does not break apart into smaller pieces. It does not leave a ghost behind. The photon simply ceases. The energy it carried now lives inside the atom as a raised electron waiting for its next move. The photon, as a distinct entity, is over. Most photons, from candles to stars to the lamp beside you, end this way. They are not brave adventurers crossing the cosmos. They are tiny packets of energy handed from one atom to the next, surviving only the brief hop between emission and the nearest absorber. A typical photon inside a star, for instance, lives only for a fraction of a billionth of a second before being absorbed by the nearest plasma particle and re-emitted in a new direction. Which raises a question. When an atom absorbs a photon and later releases a new photon of the same energy, is it the same photon or a different one? An atom absorbs a photon. A moment later, the atom releases a photon of the same energy, heading in some new direction. From the outside, it looks like the photon survived the encounter, bounced off the atom and continued on its way. But look more closely, and something stranger is happening. The photon that went in was destroyed. Its energy was taken up by the atom, lifting an electron to a higher energy level. For some time, however brief, there was no photon. There was only an excited atom. Then the electron fell back down, and a new photon was emitted. This new photon carries the same energy as the one that came in, because the electron fell back through the same gap it was pushed up through. But it is a freshly made photon, produced in the emission process, not the same particle that was absorbed, or so it seems. Here is where things get slippery. In quantum mechanics, particles of the same type are not just similar, they're identical in a way that ordinary objects never are. Two electrons are not like two grains of sand, distinguishable in principle, if only we could look closely enough. Two electrons are genuinely interchangeable. There is no experiment, no measurement, no quality you can point to that would let you say, this electron is the one that was here before, and that electron is the one that arrived later. The universe does not label them. They have no serial numbers. They have no history engraved on them. The same is true of photons. A photon of a particular energy, moving in a particular direction, with a particular polarization, is indistinguishable from any other photon with those same properties. If an atom absorbs a photon and then emits a photon with matching properties, there is no fact of the matter about whether it is the same photon or a new one. The question has no answer, not because we cannot find out, but because nature does not distinguish. This is hard to accept, because our intuition says everything has an identity. Your pen, if it leaves your desk and comes back, is still your pen. It has the same scratches, the same ink stain, the same specific history. But photons do not have that kind of history. They do not carry a record of where they have been. They are entirely defined by a short list of properties, and any two photons sharing those properties are, in the strictest sense, the same particle. So when you ask whether the re-emitted photon is the same as the absorbed photon, physics shrugs. The question assumes a kind of identity that photons do not possess. It is a little like asking whether the number 3 that appears in one equation is the same 3 that appears in another equation. The 3 itself has no identity. It is the same 3 everywhere. This has practical consequences. In the interior of a star, photons are constantly being absorbed and re-emitted as they fight their way from the core to the surface. A photon released at the core of the Sun takes on average tens of thousands of years to reach the surface, because it is absorbed and re-emitted roughly 1 trillion times along the way. From the outside, it looks like the light is slowly diffusing outward. From the inside, it is more like a rapid series of deaths and rebirths, with no photon in the process having any continuous existence. By the time sunlight reaches you, the photons entering your eye are fresh. They were created at the surface of the Sun only 8 minutes before. The energy they carry, however, was born deep in the core long before. That energy has passed through countless photons to reach you, and no single one of them made the whole trip. This idea of photon indistinguishability has a strange and beautiful test in the laboratory. It is called the Hong-ou-Mandel effect, and it shows something about photons that has no parallel in the ordinary world. Here is the setup. 2 photons arrive from 2 separate sources at a kind of partially silvered mirror that scientists call a beam splitter. When one photon hits the beam splitter, it has a 50% chance of passing through and a 50% chance of bouncing off at a right angle. This is ordinary quantum behavior. A single photon does not know which way it is going. It is a probability, not a fact, until it is detected. Now send 2 photons into the beam splitter from opposite sides, both arriving at the exact same instant. Each photon has its own 50% chance of passing through and its own 50% chance of reflecting. If you treat them as independent, you would expect 4 possible outcomes with equal probability. Both pass through and end up on the opposite sides they came from. Both reflect and return the way they came. One reflects while the other passes through, so they both end up on one detector. The mirrored case of that, they both end up on the other detector. Classical reasoning says that in half the cases the photons should separate and go to different detectors, and in half the cases they should end up on the same detector. Run the experiment many times and you should get a 50-50 split. That is not what happens. If the 2 photons are truly identical, matching in every respect, frequency, polarization, timing, then the 2 outcomes where the photons go to different detectors cancel each other out through quantum interference. They simply do not occur. Every single time the experiment is run, the 2 photons come out of the beam splitter together, on the same side. They refuse to separate. The photons bunch. This result has been measured thousands of times. It only works when the 2 photons are truly indistinguishable. The moment you introduce any difference between them, say by changing the colour of one slightly, or by making them arrive at slightly different times, the interference weakens, and some of the experiments show the photons separating after all. Tune the difference higher, and the bunching disappears entirely, and the photons behave as independent particles should. The Hongo-Mandel effect is, in a sense, the experimental proof that photon indistinguishability is real. It is not just a philosophical claim about particles having no serial numbers. It is a physical fact with measurable consequences. 2 identical photons behave as a single collective entity at the beam splitter. 2 distinguishable photons do not. This tells us something profound about what photons actually are. They are not little billiard balls made of light. They are excitations of an underlying field, the electromagnetic field, and when 2 excitations are identical, they merge in a way that individual objects never could. Each photon is less like a separate thing, and more like a ripple on an ocean, where 2 identical ripples meeting at the same spot combine into a shared pattern rather than jostling past each other. This picture of photons as ripples on a field opens up an even stranger idea. If photons are ripples, then there must be a medium for them to ripple in, and that medium, the electromagnetic field, is present even when no photons are there. Before a photon exists, the electromagnetic field exists. The field fills all of space, always, even in the emptiest corners of the deepest vacuum. You cannot get rid of it. You cannot turn it off. It is part of the structure of reality. A photon is simply a particular kind of disturbance in this field, a localized ripple that carries energy from one place to another. This picture is counterintuitive, because when you look around, you do not see anything. Empty space looks empty, but empty space is not empty in the sense of being nothing. It is empty in the sense of being unexcited. The electromagnetic field is there, quiet, at its lowest energy state, waiting. When an atom gives up some of its energy in the form of a photon, what actually happens is that the atom causes a ripple in the field, and that ripple travels outward at the universal speed limit, eventually arriving at some distant atom where it's absorbed. Think of the field as an invisible, infinite, perfectly elastic material filling everything. A photon is a pluck on this material, a vibration with a specific wavelength and direction. The pluck travels, and when something catches it, the energy is transferred and the pluck ends. This picture helps clarify several things that have been puzzling us. It explains why photons are identical. They are identical because they are all the same kind of ripple on the same field. It explains why re-emission does not produce the same photon. Each emission is a new pluck, and it explains why photons can appear and disappear so cleanly without leaving debris. They are patterns in a medium, not objects made of stuff. When the pattern fades, there's nothing left to leave behind. It also opens up a startling possibility. If the field is always there, then the field has some energy even in its quietest state, not zero energy. The lowest possible energy, which turns out to be not quite zero. And that lowest energy comes with tiny fleeting fluctuations. Even in a perfect vacuum, the electromagnetic field jitters. It trembles at the smallest scales, producing transient disturbances that flicker in and out of existence faster than any clock can catch. These transient disturbances behave a lot like photons, except they do not live long enough to travel. They pop up, exist for a stunningly brief instant and vanish, all within the margin of the uncertainty principle, which allows temporary violations of energy conservation as long as they are short-lived enough. We call these virtual photons. They are a bookkeeping device, a way of accounting for how electromagnetic forces actually work at the smallest scales, but they also seem to represent something real about the nature of the vacuum. Every magnet on your refrigerator, every electric current in every wire around you, every electrical force between every charged particle in the universe is mediated by these virtual photons. They carry the electromagnetic interaction. When two electrons push each other apart, they are trading virtual photons back and forth, and the trade is what produces the force. The photons involved are not the long-lived kind that streak across the cosmos for billions of years. They are brief, temporary, never directly detectable, and yet their existence is what makes electromagnetism work. This distinction between real photons and virtual photons turns out to be one of the most important in all of physics, and it changes how we answer the question of whether photons live forever. A real photon is a ripple in the electromagnetic field that carries a definite amount of energy across a definite distance, moves at the universal speed limit, and can in principle be detected by an instrument. Every photon of sunlight is a real photon. Every photon in a radio broadcast is a real photon. Every photon from a distant galaxy is a real photon. These are the ones we have been discussing all along, the ones that live for potentially billions of years. A virtual photon is different. It is a temporary, short-lived disturbance in the same field, but it does not obey the usual rules that real photons obey. Its energy does not have to match its wavelength in the standard way. Its speed does not have to be the universal limit. It cannot be directly detected, only inferred through its effects, and it exists for only a fleeting instant, borrowing energy from the vacuum and paying it back before anyone can notice. Virtual photons are what carry the electromagnetic force between charged particles. When two electrons come near each other and feel a mutual push, what is actually happening, according to quantum field theory, is that they are exchanging virtual photons. One electron emits a virtual photon, the other absorbs it, and the exchange produces a change in momentum that we perceive as repulsion. Same thing between an electron and a proton. Virtual photons pass back and forth, pulling them toward each other. This is a strange picture because the virtual photons in the middle of these exchanges are not really out there travelling freely. They are a piece of the mathematics, a term in the equations, a way of calculating what happens when charged particles interact. But the calculations work spectacularly well. The results of virtual photon exchange match every experiment ever performed on electromagnetic forces down to incredible precision. Whatever virtual photons really are, the math that treats them as temporary field disturbances makes predictions that reality agrees with. The lifetime question shifts when we consider virtual photons. Real photons can last for billions of years. Virtual photons last for essentially no time at all, maybe a billionth of a billionth of a billionth of a second, just long enough to carry a force between two particles before flickering out. Their short lifespan is built into what they are. They're not born to travel. They're born to mediate an interaction and then disappear. But here is the deep point. The same field produces both. The electromagnetic field is capable of supporting both long-lived ripples that fly across the universe and short-lived fluctuations that barely exist. The difference is not in the field. It is in the conditions under which the disturbance is created, and whether the disturbance can sustain itself as a free-flying wave, or whether it is trapped in a momentary exchange between particles. This means that when we say photons might live forever, we're specifically talking about real photons, the ones that have been emitted into free space and are free to travel. The virtual photons that mediate every electromagnetic force around you are constantly being born and dying, and have been doing so since the beginning of the universe. They are, in their way, the most common photons of all, but they never live long enough to travel, and they never get the chance to become the kind of photon we can call eternal. So the question of photon immortality applies to one specific kind of photon, and the rules that govern whether that photon survives are different in interesting ways from the rules that govern its virtual cousins. There is a small mystery that every student eventually runs into. The universal speed limit is supposed to be absolute. Light is supposed to travel at that speed in every situation, for every observer, and yet, when you shine a flashlight into a block of glass, the light moves slower inside the glass than it did in the air. When you shine a laser into water, the same thing happens. Inside denser materials, light appears to crawl, sometimes to less than half the speed it had in vacuum. How can this be? Is the photon breaking the universal rule? Is it actually slowing down? The answer is yes and no, and the resolution is beautiful. A photon by itself, in empty space, always travels at the universal speed limit. That rule does not bend. But when you send a photon into a dense material like glass, the photon does not travel through the glass the way a bullet travels through air. The glass is full of atoms, and those atoms interact with the photon continuously. Here is what actually happens. The photon enters the glass and very quickly is absorbed by an atom. The photon is gone. The atom is now excited, carrying the energy. A moment later, the atom emits a new photon in the same direction, with the same energy. That photon travels a tiny distance, encounters the next atom, is absorbed, excites that atom, and is re-emitted. And so on, thousands upon thousands of times, all the way through the glass. Each of these tiny photons between absorptions is travelling at full speed. Inside the gaps between atoms, the universal speed limit is not violated, but the total time it takes for the light to cross the glass is longer than it would be in a vacuum, because every absorption and re-emission takes a tiny non-zero time. Add up all those tiny delays, and the light's overall progress is slower than the universal speed. From the outside, looking at the glass as a whole, it looks like the light is moving slowly through the material. From the inside, looking at each individual photon, nothing is moving slower than it should. The apparent slowdown is a collective effect, an average over 1 trillion tiny absorption events, not a change in the fundamental speed of any actual photon. This picture has consequences for our question about photon lifespans. Inside a dense material, no photon lives long. Each one is born, travels a molecular scale distance, and dies in an absorption event. The light that emerges from the far side of the glass is not the light that entered. It is a long chain of successive photons, each one a fresh emission, carrying the same energy and direction, but none of them the same as the photon that started the chain. In this sense, light inside a material is the opposite of immortal. It is a parade of births and deaths, happening so quickly and so uniformly that the overall pattern looks continuous, but every link in the chain is a new photon, a fresh ripple in the field. It is a strange thought that the shaft of sunlight hitting a window is, in a sense, reborn thousands of times as it passes through the glass. And the photons that exit the window on the other side are not the same photons that entered. They carry the same message, the same energy, the same colour, but they are freshly minted at the far surface. Light, when it travels through matter, is less a journey and more a relay race. Step outside the glass, though, and the photon returns to its solitary, free-flying nature. Once in open space again, it can travel for as long as the universe allows, carrying information encoded in its wavelength, its polarization, and its direction. Every photon carries a property that the ancient study of light never imagined. It is called polarization, and it is one of the clearest clues that photons are more than just energy packets. They have structure, a kind of orientation in space. Imagine looking straight down a beam of light, along its direction of travel. As the light wave oscillates, it vibrates. The vibration is in the electromagnetic field, and that vibration has a specific direction, at right angles to the photon's motion. For some photons, the vibration is vertical, up and down. For others, it is horizontal, side to side. For others, it traces out a diagonal, or a circle, or an ellipse. This direction of vibration is the photon's polarization. Most natural light, like sunlight or lamplight, is a mix of photons with all possible polarizations, jumbled together in no particular pattern. You do not notice this, because your eyes cannot tell the difference between a horizontally polarized photon and a vertically polarized one. Both look the same. Both have the same color. But introduce a filter, a special kind of material that blocks certain polarizations and lets others through, and you can sort photons by their orientation. Hold a polarizing filter up to the sky and rotate it. You will see the brightness of the light change as you rotate. Sunlight scattered off the atmosphere is partially polarized, and the filter is letting through only the photons whose vibration direction matches its own. What does this tell us about photons? It tells us that a photon is not a simple point of energy. It is a structured thing. It has an internal property that can point in different directions, and that property survives the photon's entire journey. A photon emitted with a particular polarization carries that polarization with it, unchanged, across billions of years of travel, unless something along the way interacts with it and changes it. This is one of the ways photons carry information. A long time ago, an astronomer might look at light from a distant galaxy and measure its polarization. The polarization tells them something about where the light came from, whether it passed through magnetic fields on the way, whether it scattered off dust clouds. The photon is not just carrying a color and a brightness, it is carrying a piece of evidence about every significant interaction in its history. More deeply, polarization is tied to something called spin. In quantum physics, particles have an intrinsic kind of angular momentum that is not the same as spinning in the everyday sense. Photons carry one unit of this intrinsic spin, and it can point in one of two directions relative to their motion. left-handed or right-handed as physicists sometimes call it. This two-state spin is what gives photons their polarization. A horizontally polarized photon is a certain combination of the two spin states. A vertically polarized one is a different combination. A circularly polarized one is one of the pure spin states by itself. This spin is never lost. A photon cannot slow its spin, cannot damp it, cannot gradually settle into a spinless state. As long as the photon exists, it carries exactly 1 unit of spin, and that spin points into one of those two allowed directions relative to its motion. This fact is tied to the deeper reason photons are massless. In the mathematics of relativity and quantum mechanics, massless particles must have this kind of fixed spin structure. A massive particle could have spin in more configurations. A massless particle is locked into just the two. This means the photon's identity is incredibly constrained. It is defined by very few things: its energy, its direction, its polarization. That is essentially all there is to say about a photon. Everything else about it is either the same as every other photon or follows directly from these few properties. This is part of what makes photons so stable. There is very little about them that could change or break. For a long time, people debated whether light was a wave or a particle. Experiments in the 19th century seemed to prove light was a wave. Experiments in the 20th century seemed to prove it was a particle. Eventually, physicists settled on the uncomfortable truth that light is both, and neither picture is complete on its own. One of the cleanest demonstrations of light's particle nature comes from looking at how photons arrive, one at a time, at a sensitive detector. If you dim a light source enough, the detector will click sporadically, each click corresponding to a single photon arriving. The pattern of these clicks is not what you would expect from a classical wave of continuously varying intensity. For ordinary thermal light, like the glow from a filament bulb, the photons arrive in a bunched pattern. If you see one photon, you're slightly more likely to see another one right after it. There are bursts of photons followed by gaps. This is called photon bunching, and it is a consequence of the quantum statistics that govern identical particles. For laser light, the photons arrive in a completely random pattern, like perfectly uniform raindrops. No bunching, no gaps, just a steady Poisson distribution of clicks. For certain special kinds of quantum light, something even stranger happens. The photons arrive in a spread-out regular pattern. If you see one photon, you are less likely to see another one right after it. The photons avoid each other. This is called photon anti-bunching, and it is impossible to explain with classical wave physics. It is a genuine quantum effect. Anti-bunching is what happens when a single quantum emitter, like a single atom or a single semiconductor quantum dot, is producing photons one at a time. After emitting one photon, the emitter needs a little while to recharge before it can emit another. During that recharge period, the emitter cannot produce another photon no matter what. This creates a gap in the stream of photons that no classical model can match. The existence of photon anti-bunching is one of the strongest pieces of evidence we have that photons are genuinely discrete, indivisible quantum objects. A photon is not a continuous flow of energy that can be divided into smaller and smaller pieces. It is a whole thing, and you either get one or you do not. When a source produces them one at a time, the pattern in the detector reveals this discreteness directly. This has direct relevance to the question of photon lifetimes. When we ask how long a photon lives, we're asking about a specific indivisible quantum entity, not a piece of a continuous stream. Each photon is a single event. Its birth is a single event. Its death, whenever it comes, will also be a single event. The photon does not gradually weaken or slowly fade in any fundamental sense. It exists, entire, until something interacts with it, at which point it ceases to be. This is part of why photon stability is so dramatic when we think about it carefully. A photon is a single, indivisible quantum excitation of the electromagnetic field. If left alone, it persists entire for as long as the universe allows. It does not lose bits of itself along the way. It does not become partially a photon. It is a photon, all of it, until the moment of its end. The cosmic microwave background photons that fill the sky around you right now are each one of these discrete, indivisible quantum objects. Each one has been a photon, entire, for 13 billion years. Each one, when caught by a detector, will end as a single quantum event, its energy transferred all at once to whatever it hit. This all-or-nothing nature of photons shapes how the universe's expansion interacts with them. A photon cannot gradually shed bits of its energy as the universe stretches. Its energy is a single property of the whole photon. So the energy lost due to cosmological redshift is something different from ordinary dissipation. A photon's energy is tied to its wavelength, and as space expands, the wavelength stretches. We have talked about this before, but there is a subtle question lurking beneath it, and if you pull on that question, you uncover one of the most unsettling features of cosmology. Where does the energy go? When a photon loses energy because of cosmic expansion, that energy has to go somewhere. Energy, after all, is conserved. You cannot just make it disappear. If a photon had a certain amount of energy yesterday and less today, where did the difference end up? The honest answer is that in the context of cosmological expansion, energy is not straightforwardly conserved. This sounds like blasphemy to anyone who learned about conservation of energy in school. But it is the real answer, and it is one of the stranger results in general relativity. In ordinary physics, energy conservation comes from a mathematical principle tied to time. If the laws of physics are the same at every moment, then energy is conserved. For most situations, this is a good assumption. The laws we use do not depend on what time it is, so energy is conserved. But for the universe as a whole, the situation is different. The universe is expanding, which means conditions at different times are different. At earlier times, the universe was denser and hotter. At later times, it is more diffuse and cooler. The global situation changes with time in a meaningful way. And when that happens, the mathematical guarantee of energy conservation fails for the universe as a whole. This does not mean energy conservation breaks down everywhere. Locally, in any particular laboratory, energy is still conserved. You cannot build a perpetual motion machine by exploiting this loophole. But if you ask about the total energy content of the entire universe, including the light filling all of space, the answer is that this quantity is not conserved. It changes. It decreases, actually, as the universe expands. So a photon's lost energy does not go anywhere. It is not transferred to something else. It simply disappears from the books. The universe is getting bigger, the photons inside it are getting stretched, and the total energy inside the universe is less than it used to be. The rules of bookkeeping that work so well in everyday physics do not apply at this scale. This is an uncomfortable result, and many physicists have grappled with how to interpret it. Some argue that there is a subtle sense in which the lost energy is absorbed by the expanding fabric of space itself. Others argue that the notion of a total energy for the universe simply does not apply, and we should stop trying to balance the books at that scale. Either way, the conclusion is the same. Photons lose energy as space expands, and there is no way to get that energy back. For an individual photon, this means that as time goes on, it carries less and less punch. A photon emitted in the earliest, hottest moments of the universe had energy enough to split atoms apart. That same photon today, after 13 billion years of stretching, has barely enough energy to warm a grain of dust. It is still a photon, still real, still travelling, but most of what made it impressive is gone. And yet it persists. The photon has not been absorbed, has not been destroyed, has not decayed. It has only been stretched. And this raises the question of whether a photon that has been drained of almost all its energy is still truly a photon in any meaningful sense, or whether it has slowly become something closer to nothing at all. The answer is the same one we encountered before. It is still a photon. It has just become a very, very quiet one. Cosmic expansion is not the only way photons lose energy. Gravity does it too, and the mechanism is worth understanding carefully, because it reveals something deep about the connection between light and space-time. Imagine a photon emitted from the surface of a very massive star. It starts out with a certain energy, a certain wavelength, heading away from the star into space. Now gravity affects everything that carries energy or momentum, and photons carry both. So as the photon climbs away from the star, it loses energy. Its wavelength gets longer. By the time it reaches a distant observer, its colour has shifted toward the red end of the spectrum. This is gravitational redshift, and it has been measured on Earth, around the Sun, and around distant neutron stars. Where does the energy go? This time, the answer is clearer than in the cosmological case. The energy goes into climbing the gravitational well. A photon in a strong gravitational field has a certain amount of gravitational potential energy, just as a ball at the bottom of a hill has less potential energy than a ball at the top. To climb out of the well, the photon trades some of its kinetic energy, which for a photon means its frequency energy, for potential energy. When it reaches a point far from the gravitating mass, it has paid a price. It arrives with less energy than it started with. The closer to the gravitating mass the photon started, the more energy it loses on its way out. A photon emitted from the surface of a normal star loses a tiny amount. A photon emitted from the surface of a white dwarf loses more. A photon emitted from just above the event horizon of a black hole loses almost all of its energy on its way out. It arrives at a distant observer as a photon with extraordinarily low frequency, barely detectable at all. At the event horizon itself, the arithmetic reaches its limit. A photon emitted from the event horizon would lose all of its energy climbing out, arriving with zero frequency, which is the same as not arriving at all. No photon emitted from the event horizon ever reaches a distant observer. The event horizon is the boundary where this is exactly the case. Closer than that, the photon cannot even start the climb. Farther than that, it can make it out, but weakened. For a photon outside a black hole, gravitational redshift is a gradual, continuous process. The photon is not absorbed, it is not destroyed. It is simply drained of some of its energy by the climb, and the drained energy is not lost to the universe in the same way that cosmic redshift energy is lost. Here, the energy is still accounted for. It is stored in the gravitational field of the massive object, and could in principle be recovered if the photon fell back in. This kind of energy loss is not a threat to a photon's immortality. The photon survives the climb. It just arrives elsewhere with less energy than it started with. If it then falls back into another gravity well, it would gain energy, its wavelength shortening on the way down. Gravitational redshift and blueshift are in this sense reversible. The photon is a permanent thing being nudged up and down in energy by the gravitational landscape it traverses. But there are photons for which the gravity question is much stranger. Photons born in the vicinity of black holes, not from falling matter but from the event horizon itself, have a status that is unique in all of physics. Every black hole, according to a theory that has held up to many checks, glows faintly, unimaginably faintly, but not at zero. A black hole is not perfectly black. It emits a trickle of radiation, and that radiation consists of photons, real photons, that come from the event horizon itself. This is Hawking radiation, and the way it arises is one of the stranger mechanisms in all of physics. Near the event horizon of a black hole, the vacuum of space is not empty in the sense you might expect. It is seething with virtual particles, those fleeting fluctuations we talked about earlier, pairs of particles and antiparticles that pop into existence for the briefest instant before annihilating each other. In ordinary space, these pairs appear and disappear without consequence. Near a black hole, something different can happen. Sometimes a virtual pair appears with one member just inside the event horizon and the other just outside. The one inside falls into the black hole. The one outside, suddenly without its partner to annihilate with, cannot do the usual bookkeeping trick of winking out of existence. It has no partner to pay its debt, so it becomes real. It becomes an actual photon, leaving the vicinity of the black hole as a permanent feature of the universe. This is a very rough way of picturing what is mathematically a more subtle process, but the essential point is that black holes radiate, and the photons they radiate are every bit as real as any other photon. They travel, they carry energy, they can be detected in principle, and they last as long as any photon lasts. The radiation is vanishingly weak for ordinary black holes. A black hole with the mass of a typical star emits so little Hawking radiation that you could wait longer than the age of the universe without detecting a single photon. The emission only becomes significant for very small black holes, which have never been directly observed. But the theoretical prediction is clear, and most physicists consider Hawking radiation to be a real feature of nature, even though we've not yet caught it in action. What makes Hawking photons unusual is their origin. They are not emitted by an atom. They are not born from the excitation of any particular matter. They are pulled out of the vacuum itself by the extreme curvature of space-time near a black hole. In a sense, they are photons made of nothing, or rather, photons made of the possibility of nothing. The vacuum always contains these virtual fluctuations, and the gravitational environment of a black hole converts some of them into permanent real photons. Once born, a Hawking photon is the same as any other photon. It travels at the universal speed limit. It carries a definite energy. It lives as long as no one absorbs it. From its birth in the neighborhood of an event horizon, it can fly off into space for billions of years, indistinguishable from light emitted by a star or a galaxy. The black hole, meanwhile, pays a price for this emission. Each Hawking photon leaving the black hole carries energy away, and since energy and mass are connected, the black hole shrinks slightly. Over incomprehensibly vast timescales, a black hole will actually evaporate entirely, converting all of its mass into a slow trickle of Hawking radiation. The entire black hole, given enough time, will disappear, transformed into a cloud of very long wavelength photons streaming outward in all directions. This is the farthest out example of photon creation we know, not from matter, but from gravity itself, not from excitation, but from space-time curvature. And the photons so produced will outlive the black holes that made them by an amount of time so vast it shames the age of the universe itself. let us try a thought experiment. Suppose you could build a box with perfectly reflective walls. Every photon that hit any wall would bounce off without being absorbed, without losing any energy, perfectly elastically every single time. Place a single photon inside this box and close the lid. What happens? The photon bounces. It hits one wall and reflects, flies across the box and hits another wall, reflects, and so on, forever, back and forth, in some complicated pattern determined by its initial direction. The photon never loses energy, because the walls do not absorb anything. It never finds an exit because there is no exit. It never decays because we've established that photons in isolation do not decay. So the photon simply persists, trapped, eternal, bouncing. This thought experiment is not purely fanciful. Very good mirrors do exist. In laboratories, scientists have built cavities where photons can bounce back and forth for remarkably long periods, each photon surviving many thousands, sometimes millions, of reflections before finally being absorbed by some tiny imperfection. In these cavities, a photon's life can stretch from the brief instant of its emission into a much longer existence, measured in seconds or even minutes, which is an eternity on the scale of individual atomic interactions. But no mirror is truly perfect. At the quantum level, there are always small probabilities of absorption, always tiny imperfections in the surface, always some leakage. In the real world, a photon trapped in a cavity eventually meets its end through one of these inevitabilities. Even the best mirror absorbs one photon out of every 100 million, or 10 billion, or some vast but finite number. Given enough bounces, every photon eventually hits an absorbing imperfection. But what if we could make the mirror truly perfect? What if the box had no imperfections at all at every scale? Would the photon really be eternal? In principle, yes. In practice, physics imposes a subtler limit even on this ideal scenario. A box must be made of some kind of matter, and matter itself is made of atoms, and atoms have finite mass and thus finite temperature. A box at any finite temperature will have its walls fluctuating slightly, which means the reflections are never perfectly elastic. There is always some exchange of energy with the walls, even in the most ideal case. The only way to have a truly perfect mirror is to cool the box to absolute zero, which is impossible, or to replace the mirror with something fundamentally non-material, which takes us outside the realm of ordinary physics. In any case we can actually build, the photon is eventually absorbed. But the thought experiment is valuable even so. It tells us that the reason photons end is not that they are fragile, or that they spontaneously decay, or that they wear out. It is that they run into something that absorbs them. Remove every possible absorber, and the photon lasts forever. Put it in open space where absorbers are very rare, and the photon lasts for billions of years. Put it in a box with good mirrors, and the photon lasts for minutes. Put it in a star, and the photon lasts for a fraction of a nanosecond before being absorbed by the next particle in line. The photon's lifespan is not really a property of the photon. It is a property of its environment. Photons, left alone, persist. They only end when something interferes, and the universe in most places has very little to interfere with them. In classical physics, two beams of light passing through each other do not interact. They pass through cleanly, without any collision, without any scattering, without any mutual influence. Shine two laser beams across each other in a dark room, and neither beam is affected by the crossing. The photons just fly through one another as if the other beams were not there. This is very different from how matter behaves. Two billiard balls cannot occupy the same space. two electrons repel each other electromagnetically from a distance and cannot pass through each other either. Matter has a solidity, exclusivity, that light does not share. The reason photons ignore each other at the classical level is that photons do not carry electric charge. Photons are the carriers of the electromagnetic force. They mediate interactions between charged particles, but they do not in the usual way interact with each other through electromagnetism directly. A photon does not see another photon as something to push against. For a long time, this was thought to be a strict rule. Photons simply did not interact, full stop. And to a very good approximation, this is still true. Beams of light pass through each other without noticeable effect, but quantum field theory predicts something strange. At extremely high energies, photons can, in very rare events, interact with each other. The mechanism involves virtual particles. When two photons encounter one another, they can briefly fluctuate into pairs of virtual electrons and positrons, and these virtual pairs can exchange particles, giving rise to an effective photon-photon interaction. It is a subtle, indirect process, and it is extremely rare at low energies. This process is called photon-photon scattering, or light-by-light scattering, and it was theoretically predicted decades before it was ever observed. Physicists calculated that the effect was real but extraordinarily weak, requiring photons of very high energy to even have a chance of being seen. In 2017, at the Large Hadron Collider in Europe, scientists finally directly observed photon-photon scattering using high-energy photons produced by heavy ion collisions. The photons were gamma rays, far more energetic than visible light, and they were produced in extreme quantities, and even then the scattering signal was faint. But it was there. Photons, under extreme conditions, can scatter off one another, just as the mathematics had predicted. This does not much change the story of photon immortality in ordinary contexts. The photons in sunlight, the photons in radio waves, the photons in the cosmic microwave background, all of them are far too low in energy to scatter off each other meaningfully. Two beams of light in open space still pass through one another without any practical effect. A photon flying through the universe does not have to worry about bumping into another photon along the way in the overwhelming majority of circumstances. But the existence of photon-photon scattering is interesting because it tells us that the strict rule is not quite strict. At sufficient energies, photons can interact, and in principle, in a sufficiently extreme environment, photons could deflect each other, could even, in the most extreme circumstances, produce particle-antiparticle pairs through their interaction. This also means that a photon travelling through a truly dense sea of other photons, like the one that existed in the earliest universe, could have a non-zero chance of interacting with its neighbours. For the early universe, this was significant. For our universe today, with photons much more spread out, it is not. The photon flying through interstellar space is effectively alone, and will remain alone for as long as its flight continues. We have established that photons do not decay in the way most particles decay. But the reasons why cut even deeper than we have explored so far, and they involve a set of principles that forbid certain transformations in general, not just for photons. Consider a photon that might try to decay into a single other particle, say, a neutrino. Could this happen? No, and the reason is simple. A photon has momentum. Whatever it decays into must carry that momentum. A single particle, like a neutrino, can in principle carry momentum, but along with carrying the right momentum, it would also have to carry the right energy and the right mass. A single particle decay has to match the initial particle's energy, momentum, and everything else. But for a photon with zero mass, decaying into a massive particle is mathematically impossible. You cannot start with zero and end with non-zero. The decay fails before it begins. What about a photon decaying into two particles? This is more promising in principle. Two particles can have a combined mass less than some threshold, and they can balance each other's momenta so that the total equals the original photon's momentum, so the balance sheet could work. But for photons, even two-particle decay is ruled out by a different principle. A photon is its own antiparticle, in a very specific mathematical sense. It has no electric charge, no baryon number, no lepton number. It cannot decay into two particles that are each other's antiparticle, like an electron and a positron, because the combined mass of those particles is much higher than the photon's energy, unless the photon is extremely energetic. For most photons, like the ones in sunlight or the cosmic background, this decay is simply impossible by energy balance. And even for very high-energy photons, the decay into electron-positron pairs is blocked by a different requirement. The photon would need something else around to make the decay possible. This is where we encounter a beautiful rule. A photon can, in certain circumstances, convert into an electron-positron pair, but only in the presence of another particle, like an atomic nucleus. The nucleus is there to absorb the leftover momentum to balance the books. Alone, in empty space, a photon cannot do this. The decay requires an external partner, so photons are protected from decay by a whole stack of principles working together. Conservation of momentum, conservation of energy, the fact that there is no lighter, allowed particle for them to become, the fact that pair production requires a nucleus, the gauge symmetry that forbids the photon from losing its stability. It is a thick wall of protection, and every part of it would have to fail for a photon to decay naturally. This is not an accident. The stability of photons is essential to the structure of physics. If photons decayed, electromagnetism would not work the way it does. Light from distant galaxies would not reach us intact. The cosmic microwave background would be corrupted. The everyday behavior of atoms and molecules, which depends on precise emission and absorption of photons, would be unpredictable. We would be living in a very different universe. Instead, we live in one where photons are, to every test we can perform, perfectly stable. They are the longest-lived particles we know. They outlast stars, galaxies, and even, in principle, the entire observable universe. They fly and fly and fly until something happens to them, and if nothing happens to them, they keep flying. Which brings us to the one remaining question that has haunted physicists for a century. What if the photon is not, after all, quite massless? What if it has a tiny mass, so small we cannot measure it, hiding at the edge of what our experiments can detect? Every few years, a new experiment pushes the upper limit on the photon's possible mass a little lower. Every time the result comes back consistent with zero. But consistent with zero is not the same as proven to be zero. There is always a small remaining possibility that the photon has a tiny undetected mass. Why do physicists care? Because even a minuscule photon mass would change everything. It would break the gauge symmetry that protects photons from decay. It would mean that photons travel slightly slower than the universal speed limit, with very low-energy photons travelling slightly slower than high-energy ones. It would change how electromagnetic waves behave over long distances. It would open the door to photon decay into lighter particles if such particles exist. The experiments to measure photon mass are incredibly creative. One method looks at the behavior of magnetic fields. If the photon has mass, magnetic fields would fall off faster with distance than they do for a massless photon. So by mapping the magnetic field of the Sun, or of Jupiter, or of a distant pulsar, and comparing to what a massless photon predicts, scientists can set limits on how much mass the photon could have. Another method uses the fact that different wavelengths of light would travel at slightly different speeds if the photon had mass. By watching for signals from distant astronomical sources, like pulsars or gamma-ray bursts, and timing the arrival of different wavelengths, scientists can look for any difference. Every test comes back finding no difference, or a difference so small it is consistent with a photon mass of 0. A third method looks at the behavior of electromagnetic fields on very large scales, measuring them across the solar system or across intergalactic distances, looking for the subtle deviations that a massive photon would produce. These tests are among the most sensitive we have, and they too find the photon consistent with being massless. The current best upper limit on the photon's mass is extraordinarily small. It is less than about a billionth of a trillionth of the mass of an electron. This is so small that even if the photon has this much mass, the effects on ordinary physics would be utterly undetectable. Light from the most distant galaxies would still arrive on schedule. Magnetic fields would still behave correctly in the laboratory. Photons would still seem, to all appearances, stable. But there is a difference between an appearance of stability and a certainty of it. If the photon really does have a tiny mass, then in the very long run, it could decay. The lifetime of such a photon would be incredibly long, far longer than the current age of the universe, but it would not be infinite. This is one of the cleanest open questions in modern physics. Is the photon truly massless, and therefore truly immortal? Or does it have a tiny mass, and therefore a finite, merely astronomical lifetime? The answer matters for the far future fate of the universe. If photons can decay, even extraordinarily slowly, then the universe will eventually contain fewer and fewer of them. The light that fills the cosmos will slowly thin out, over timescales that dwarf anything we can easily imagine. Eventually, in the very distant future, the last photon will blink out, and the universe will be truly, permanently dark. If photons are truly massless and truly stable, then even in the far future, photons will continue to exist. They will be redshifted to enormous wavelengths. They will be incredibly diffuse. But they will still be there, quietly persisting, bearing witness to whatever is left of the cosmos. Suppose, tomorrow, an experiment found definitive evidence that the photon has mass. Not a huge mass, but a small, measurable one. What would we have to rewrite? The first thing we would have to give up is the U1 gauge symmetry that governs electromagnetism. This is not a small thing. Gauge symmetries are the scaffolding of modern physics. They give us our fundamental forces and our conservation laws. Losing the U1 symmetry would force a major restructuring of how we think about electromagnetism. The second thing we would have to change is our picture of the photon itself. A massive photon is a different kind of particle from a massless one. It has a rest frame. It has proper time. It has a different set of allowed polarizations. A massless photon has two polarization states, the familiar horizontal and vertical, or left and right circular. A massive photon would have three, including a new longitudinal polarization that does not exist for massless light. This third polarization would be detectable, at least in principle. It would show up in certain kinds of experiments as an extra signal that massless photons cannot produce. No such signal has ever been observed, which is one of the strongest arguments against a massive photon. If the longitudinal mode existed, it should have shown up by now in some experiment somewhere. Beyond these foundational changes, a massive photon would have practical consequences that would ripple through everyday physics. Electromagnetic waves would not propagate indefinitely in vacuum without loss. They would weaken over very long distances. Radio communications across interstellar scales, if we ever attempted them, would face a fundamental limit. The cosmic microwave background would show deviations from its current perfect thermal spectrum, because photon mass would affect how the radiation evolves over billions of years. Every one of these consequences has been searched for, and everyone has come up empty. The current constraints are so tight that even if the photon has mass, the effects are far too small to notice in any practical situation. Your radio still works, your eyes still see, the stars still twinkle. None of this would change even if the photon had a mass at the edge of what current experiments can rule out. But the deep structure of the theory would change, and with it, our understanding of what the universe fundamentally is. A massive photon is a very different thing from a massless one, not in its behavior, but in its nature. The question of whether photons are truly massless is, in this sense, a question about the deepest symmetries of the universe. Most physicists today think the photon is truly massless. The evidence is overwhelming. Every test has come back with results consistent with zero mass. The theory that says photons are massless, quantum electrodynamics, is the most precisely tested theory in the history of science. Its predictions agree with experiment to more decimal places than any other theory we have. If the photon has a mass, the effects of that mass are below the precision of even our most careful measurements. But science is not about certainty. It is about the best evidence we currently have, and the current best evidence says the photon is massless, stable, and immortal, in the sense that no internal process can cause it to decay. For all the ways the universe might kill a photon, spontaneous decay is not one of them, which means that the photon's fate in any given case is always tied to its environment. The photon does not die of natural causes, it dies when something kills it. A photon carries information. Its frequency tells you something about its origin. Its polarization tells you something about what it has passed through. Its direction tells you where it came from. Every photon that arrives at your eye carries a piece of evidence about the universe, and the evidence is genuinely preserved across its journey. This is one of the quietest miracles of photon behavior. Over billions of years, a photon does not lose the information it was born with. Its frequency might be redshifted by expansion or gravity, but the pattern of its polarization remains. The pattern of its phase, the precise alignment of its wave remains. Any entanglement it might have with other photons, if it was produced that way, remains. The information encoded in the photon at the moment of its birth is still there when it arrives, however much later. This preservation is not automatic. In other physical systems, information can get lost. A footprint in sand can be erased by the wind. A memory can fade. A written record can decay. But a photon traveling through empty space cannot forget. It has no internal mechanism to lose what it was given. This is why astronomy is possible. When we look at distant galaxies, we're reading information that photons carried to us across incomprehensible stretches of space and time. The light from a galaxy 10 billion light-years away tells us what that galaxy was like 10 billion years ago. The light has not degraded, it has only stretched. The information is still there, just encoded at different wavelengths than when it was emitted. This raises a deep question that physicists have argued about for decades. When a photon is finally destroyed, whether by absorption, or by falling into a black hole, where does its information go? For absorption, the answer is relatively clean. The photon's information gets transferred to the atom that absorbed it. The atom now carries the energy and, in various subtle ways, the information. It might re-emit a new photon carrying some of the original information, or it might dissipate the energy as heat, which spreads the information over many particles in the surrounding material. Either way, the information is not lost from the universe. It is rearranged, spread out, but still there. For a photon falling into a black hole, the question is much more fraught. The black hole swallows the photon, and the information seems to disappear inside the event horizon, inaccessible to anyone outside. If the black hole eventually evaporates through Hawking radiation, as we believe it does, the radiation that comes out seems to be random, carrying no information about what fell in, so the information appears to be lost. This apparent loss is called the information paradox, and it is one of the biggest unsolved problems in physics. Most physicists believe the information must be preserved somehow, because information conservation is a deep principle of quantum mechanics. But exactly how it is preserved in the case of black hole evaporation is not yet fully understood. Recent theoretical work suggests that the information is slowly encoded in subtle correlations within the Hawking radiation, emerging over the lifetime of the black hole's evaporation. But the details are still being worked out. For photons in ordinary circumstances far from black holes, information is simply and robustly preserved. A photon is a faithful messenger. It carries what it was given, without embellishment, without forgetting, without decay. It is a perfect vessel for sending information across the cosmos, and this makes it extraordinary in a universe full of things that lose their shape. Let us look far ahead, trillions of years into the future, far beyond anything we can easily picture. What happens to photons in the long haul? The universe has a timeline stretching out into the deep future. Stars are formed from clouds of gas. They burn for millions or billions of years. They die, some as supernovae, some as white dwarfs, some as neutron stars, some as black holes. New stars form from the debris. This cycle continues, but it is not infinite. Eventually the universe runs low on the raw material for star formation. Hydrogen gets consumed. Fewer and fewer new stars form. A few trillion years from now, the last new stars will have formed. A few trillion more years after that, the last of those stars will run out of fuel and die. The galaxies will become dark. The cosmos will be lit only by the slow cooling of stellar remnants, which fade over vastly longer timescales. During this era, what happens to photons? Fewer are being produced because fewer stars are shining. The photons already emitted continue to travel, many of them having been released billions of years earlier. They're still flying through intergalactic space, redshifted and dimmed but intact, reaching out into the future. Some are being absorbed by remaining matter, some are being lost to the expansion of the universe, stretched to ever longer wavelengths. The cosmic microwave background, those ancient photons from the universe's infancy, continues to exist, continues to stretch, continues to cool. Its temperature drops further, its wavelength grows longer, it becomes more diffuse, its photons more spread out, but it does not disappear. It is still there, silently filling space. Over timescales of many trillions of years, even the remnants of dead stars, the white dwarfs and neutron stars, slowly cool and fade. They emit photons as they cool, photons that stream out into space and join the ever-growing population of unabsorbed light travelling through the empty cosmos. Eventually, these remnants cool to the point where they no longer emit detectable amounts of light. At the even longer timescale, black holes evaporate. This is the timescale that makes everything else look brief. A stellar mass black hole evaporates over a time that has so many zeros in it that the human mind cannot really pass the number. But it does evaporate eventually, converting all of its mass into Hawking radiation, a trickle of very long wavelength photons streaming outward. By this point in the universe's history, the cosmos is a very strange place. There are no stars, there are no galaxies, or at least no galaxies as we would recognize them. There are no planets. There is only a vast expanse of empty, expanding space, filled with extremely diffuse, extremely low-energy photons, along with whatever stable particles happen to remain from earlier eras. The universe is cold, dark, and mostly empty. But the photons are still there. Some of them are ancient, from the cosmic microwave background stretched out across timescales so vast they hardly make sense. Some are from the last stars that ever shone. Some are from the evaporation of the last black holes. All of them are redshifted to wavelengths larger than anything we currently observe, carrying energy so small it approaches but does not reach zero. In this far future, photons are the last coherent things in the universe. They persist when everything else has either decayed or dispersed. They carry the only remaining information about what came before. They are the final witnesses, flying forever through an increasingly empty void, unless they eventually also succumb to whatever fate time has in store. As time stretches into the deep future, the universe does not just become dark, it becomes dilute. The photons that remain are spread across ever larger volumes of space, their density dropping towards zero, even as their individual existence persists. Picture this carefully. In the present universe, the cosmic microwave background fills every cubic centimetre of space with about 400 photons. That is a lot. Every cubic centimetre of the universe, including the one at the tip of your finger right now, contains hundreds of photons from the early universe, each of them a genuine ancient messenger. Fast forward a few billion years, the universe has expanded, the volume of space has grown. The same photons are now spread across more space, so the density drops. Each cubic centimetre contains fewer photons because the total number is the same, but the space is larger. Fast forward trillions of years, the universe is much bigger. The photons are even more spread out, perhaps only 1 or 2 per cubic centimetre. Eventually far less than 1 per cubic centimetre. Most cubic centimetres of space contain no photons at all, and the photons are clustered, relative to a random point, at some great distance away. Fast forward to incomprehensibly long timescales. The universe continues to expand. The density of photons drops arbitrarily low. The average distance between any one photon and its nearest neighbour grows to vast, unimaginable scales. A photon from the cosmic microwave background in the far future might be alone in a region of space many billions of light years across. At this point, the photons are still photons, still real, still existing, still travelling. But they are so sparse that any given region of space is effectively empty of light. An observer in that region, if one could somehow still exist, would see nothing. The sky, such as it was, would be completely dark, not because the photons had died, but because they had been diluted beyond any ability to gather them. This is what a universe in its far future looks like. Not empty, strictly, but effectively empty, sparsely populated by photons that are so spread out and so low in energy that they cannot be collected into any meaningful signal. The photons persist, but their collective influence on anything is vanishingly small. And the expansion continues. Space keeps growing. Photons keep getting more spread out. Their wavelengths keep stretching. Their density keeps dropping. There is no end to this process within ordinary physics unless the expansion itself changes its behavior at some point. This is what eternity looks like for the photon, not a frozen, unchanging existence. A slow, continuous thinning, forever and ever, without end. The photon does not die, but its world becomes less and less populated. The universe becomes a home for photons who have no one else to meet, no surface to strike, no detector to click. They are alone, and becoming more alone with every passing eon. There's something haunting about this picture, and there is also something beautiful about it. A photon is the longest lived thing we know. Its existence outlasts everything else. When the last star has died, when the last black hole has evaporated, when all the matter in the universe has either decayed or been scattered beyond recognition, the photons will still be there, flying, witnessing the silence. There is one more piece of the puzzle. The expansion of space is not uniform in time. For most of the universe's history, the expansion was slowing down as the gravity of matter pulled everything together against the outward rush. But in the last few billion years, something has changed. The expansion is speeding up. Something is pushing space apart faster than matter can pull it together. We do not know exactly what this something is, and we call it dark energy for lack of a better name. If the expansion continues to accelerate, something strange happens to the cosmos. Distant galaxies recede from us faster and faster. Eventually they recede faster than the universal speed limit, in the sense that the distance between us and them grows faster than light can cross. When this happens, we can no longer see them. Light from those galaxies can never reach us. They cross a kind of cosmic horizon and become inaccessible. This cosmic horizon is similar in some ways to a black hole's event horizon, but it surrounds us on all sides, expanding outward. And it has consequences for photons that a black hole's horizon does not have. A photon emitted by a distant galaxy, when that galaxy is close enough to be within our cosmic horizon, can reach us. A photon emitted by the same galaxy, after it has crossed outside our horizon, cannot. The photon is still flying. It still exists. But the space between us is expanding too fast, and the photon will never arrive. In this future, every pair of objects in the universe eventually loses contact. As the horizon tightens, things we can see today will vanish from our sky. Galaxies will fade out one by one, not because they are dying, but because they are receding faster than their light can carry the message to us. Eventually, only our own galaxy will be visible, isolated in a darkening cosmos. For a photon emitted in this future era, the implications are strange. A photon emitted from a galaxy that has just crossed the horizon is now flying through space that is expanding faster than the photon can outrun. The photon is travelling at the universal speed limit, but the space between its point of emission and any potential destination is growing faster than the photon can close the distance. The photon will never arrive anywhere. It is condemned to fly forever, never meeting anything. This is a kind of functional immortality. The photon does not die. It cannot be absorbed, because there is nothing within reach to absorb it. It cannot be detected, because no detector can be reached. It just flies through space that is expanding around it, approaching but never quite arriving at a destination that itself keeps receding. In a sense, the accelerating expansion of the universe creates a new kind of eternal photon. A photon trapped not in a mirror box, but in the runaway growth of space itself. Such a photon is alone, travelling through a cosmos that is becoming emptier and emptier around it, its wavelength stretching, its energy approaching zero, its journey endless. This is the far edge of the question of photon immortality. In this scenario, the answer is clearer than anywhere else. Photons really do last forever. They cannot be stopped because stopping requires an encounter, and encounters become impossible. The universe has arranged for its light to outlast everything else, including the ability of anything to receive that light. After all of this, what is the answer? Photons are, as far as we can tell, truly immortal. A photon released into empty space, if nothing interferes with it, will continue to exist indefinitely. No internal process causes it to decay. No natural wear erodes it. It is, by the laws of physics as we currently understand them, permanent. But the universe is full of things that can end a photon. Atoms absorb them, black holes swallow them, the expansion of space stretches their energy towards zero, dilutes their presence, and eventually moves destinations beyond their reach. Most photons ever produced in the universe have already ended, absorbed by something along their journey, their energy transferred into whatever they hit. A smaller number are still in flight, some of them having been flying for billions of years. The photon is not immortal because it has a protective shield or because it has no weaknesses. The photon is immortal because it has no internal clock. It does not age. It does not wear out. Whatever happens to it will happen from outside, not from within. It exists, entire and unchanged, until something else ends it. This is a rare property in the universe. Almost every other particle has either a finite lifetime or some way to fail. Neutrons outside of atomic nuclei fall apart in minutes. Unstable atoms decay. Complex structures break down. Even protons, according to some theories, might eventually decay over timescales far beyond the current age of the universe. But photons, as far as we can tell, are truly stable. They are the one thing in physics that does not, by its own nature, come to an end. The meaning of this is strange. The universe contains many things that feel permanent. Rocks seem permanent on human timescales. Mountains seem permanent on longer ones. Stars seem permanent on even longer ones. But none of these are truly permanent. All of them are changing, aging, being built up and torn down by processes we can trace and understand. A photon is different. A photon genuinely does not change with time from its own point of view. It does not experience duration. It does not accumulate wear. From the moment it is born to the moment something ends it, it is exactly the same entity. If nothing ends it, it remains exactly the same forever. This is, in some sense, the quietest and most radical fact about photons. They are the things in the universe that come closest to being eternal, not just long-lived, but genuinely outside the process of aging. In a cosmos where everything seems to have a timeline, photons do not. When you look up at the night sky, you are seeing this directly. The light reaching your eye from a distant star was emitted long ago, and has been travelling the whole time. It has not weakened in any fundamental sense. It is exactly the same photon it was when it left the star, except for the stretching of its wavelength by cosmic expansion. Its frequency has dropped a little. Its direction is the same. Its polarization is the same. It has carried faithfully the information it was given. And when that photon enters your eye and is absorbed by a molecule in your retina and triggers a signal that eventually becomes a perception, the photon ends. Its long journey, perhaps crossing thousands or millions of years of travel, closes in a single, instantaneous event inside a cell in your body. The photon is gone. The information it carried is now yours. This is the life of a photon. Born in an atom, flying through space at the universal speed limit, unaging, unwearying, until something finally meets it and ends its journey. For most photons, this meeting happens quickly. For some, it takes billions of years. For a few, in a future universe of receding horizons and cooling remnants, it may never happen at all. Photons are the closest thing we have to immortal particles. And the light you see right now is a living piece of that immortality, briefly arriving in your eye before giving itself up to become a signal you experience as sight